What about nuclear effects? Well, I showed on the video that the hydrogens are indeed vibrating, and so are the deuteriums. So one can calculate what the nuclear fusion rate, if you're just sticking to straight nuclear DD fusion, what that is based on standard nuclear physics, where delta is the excursion, the maximum approach, essentially, of the deuterium atoms. This is something we can calculate, and in fact, it's the same delta that you use to explain the superconducting properties at low temperatures. So we know that delta is about right. It's not that large. It's about a half an angstrom, which sounds like it's large, but in fact, if you calculate the nuclear reaction rate based on that formula, which is taken from the nuclear physics literature, then you can calculate the fusion rate as a function, deuteron pairs per second, as a function of the DD bond overlap along those channels that connect tetrahedral sites. And what you can show is that the overlap of deuterium wave functions calculated from first principles never gets above 33%. And so this is the entire range in which you can expect any significant bond overlap. And based on that, the fusion rate never gets above low orders of magnitude, which, again, consistent with Peter's own theory, are consistent with Jones's early work. In other words, very low ranges of neutrons. So you can't possibly have enough neutron production or fusion, nuclear fusion, to explain heating effects. All right. Are there other things you can do? Well, we studied silver alloys, for example, and we found subtle but nonetheless significant increases in the DD overlap between tetrahedral sites. For example, when we alloyed silver and palladium to about 25%. We also looked at gold. What we were trying to do was to see whether we could predict that by alloying, you might actually enhance the DD fusion rate to, let's say, reach the maximum value of those limits that I showed in the earlier. So you could actually produce a measurable neutron increase. Here's the case of gold. And again, I mean, you have to look at these very carefully, but there's a slight increase when you go to gold. Well, that's also allows us to predict from standard nuclear physics what the increase, all other things being equal, assuming you can load palladium, silver, and palladium gold to the same degree you can load pure palladium, then the fusion rate should go up by around 2 orders of magnitude for these particular concentrations of silver and gold. Now, that's interesting because it turns out that in the literature, and we discovered this after the fact, actually Brian Ahern discovered it, brought my attention to the papers, it's these same guys, Stritzker, who had worked on the earlier, found that if they alloy palladium with copper, silver, and gold, indeed, the transition temperature increases markedly for those same concentrations of alloying. In other words, the transition temperature for superconductivity goes from 9 degrees, almost doubles for the case of silver. And that's a very interesting prediction that one can make, that if you study palladium-silver alloys and you do everything the same, you should see an increase in low-level nuclear effects, assuming you've measured them properly, and as I'll show you, excess heat, or what appears to be excess heat. All right, now let's get back to the potential surface. Here again is the potential surface. What I've labeled here is the tetrahedral symmetry, which is reflected by these atomic positions, and then what happens when these deuterium atoms rotate, come together, and recombine to form dideuterium, and then go shooting out of the system. And this happens many times per second. And every time this happens, the system rolls downhill. This is a famous Mexican hat that you've all seen in elementary particle physics and cosmology and so on and so on. This lower energy state, which has this D2H symmetry, broken symmetry. Now, interestingly enough, that figure is roughly the figure for the bond, twice the bond energies of 2 hydrogen molecules. Now, to understand whether this has anything, if at all, to do with the so-called excess heat, you have to keep in touch with the progress that's been made in the understanding of our most elusive substance on the planet, namely water. This is just one of several papers that have been published in the last 2 years on the interatomic structure of water. Now, one of the things that called my attention in these papers was the fact that the tetrahedral coordination of hydrogen and deuterium is very important, whether you're talking about bulk palladium or the 110 surfaces of nickel. What is the structure of water? Well, the latest evidence for it is that, in fact, it's tetrahedral, and that the hydrogens arrange themselves with tetrahedral coordination with respect to each other, and that, if you look at this paper, for example, a large part of what we call the latent heat of water, which is the energy that distinguishes water from the vapor, which is a large number, lies not in the localized HO bonds, but in fact in long-range hydrogen bonds. Now, what happens when you electrolyze water in a cold fusion experiment? What you do is you break the HO bond correlations. You send the hydrogens to the cathode, you send the oxygens to the anode. But you do not break the hydrogen-hydrogen bond correlations at the surface of the cathode. And in fact, my thesis is that what happens is when you reestablish these tetrahedral hydrogen-hydrogen bonds inside the material, you recapture a large part of the latent heat of water. Now, if this is true, then there's some predictions you can make. One is that once you've released the heat, the hydrogen and oxygen, which is now molecular, which comes out of the system, is going to be in a different entropic state from the hydrogen and oxygen that you would ordinarily get if you just electrolyzed water straight. And therefore, it should be very difficult to recombine hydrogen and oxygen to liquid water. That's why I asked that question this morning in the closed cell experiments, how much water do you regain? Because if you've reformed the hydrogen-hydrogen bonds, which account for the latent heat of water, then you can't get it twice unless you allow the system to communicate with the vast thermal thermal bath that is the rest of the universe. So what one can do then is one can design something like this. One can design a water engine